let us start after the holiday. I want to first remind you about the last class before we continue. So a reminder of what we did. So we were studying phase transitions. So studying phase transitions. And now phase transition. Of course, for systems that are translation invariant, there is a connection to the pressure. But more generally, phase transitions will be, when I say phase transitions, what I mean is that that there is different thermodynamic limits for the local Gibbs measures. And then the way that we show this is by the strategy is something that is called the Pyros argument. The Pyros argument, right? And for the Pyros argument, I will not do it again, but for the Pyros argument to work, we need basically two things. We need to define some geometric objects that we call contours. And for the nearest neighbor Ising model, these contours were the connected components. The contours were a pair. The contours for a configuration, sigma, were a pair, where C is a connected component of the incorrect points of the configuration, the boundary of the configuration, and sigma C is the configuration restricted to C. Okay, so these were the geometric objects, and then we showed that the number of contours such that 0 is in its volume and the size of the support is equals to n, and this is less than the exponential of some constant times n, and this constant only depends on d. We proved this. And the second ingredient is an energy estimate. So what happens to the energy when you erase one of the contours, and by the erasing procedure we have a map tau that depends on the contour. And it's from, let me change the minus boundary condition. So, and what this do is, this gives me sigma x. If x is in the minus interior or outside the volume of gamma, it's minus sigma x if x is inside the interior, plus of gamma, and minus 1 if x is in the support of the contour. Okay, And what we showed, okay, we showed the following bound for the plus boundary condition, but in the case where there is no field, okay, there is no magnetic field, it's just the same to work with the plus or the minus boundary condition. And we showed that, oh, and this erasing procedure depends on gamma A minus contour. Okay, this is important. And then we showed that if gamma is a contour that's on the family of gamma sigma, where gamma sigma is the family of contours associated to sigma, then this difference is larger than J times the support, okay? There is no magnetic field. And then what happens is that to analyze the phase transition with a spatially dependent magnetic field, what we did was the following. First, we want to study the system with a magnetic field that is not constant, that is spatially dependent, and it's a very specific one. This is the one. It's a magnetic field defined through this expression right here, delta, every time x is not 0, okay, so from 0, and both these constants, delta and h star, are positive, okay, positive real numbers. So this term will modify the Hamiltonian, right? And by using the form of the Pyros argument, what we need to study, what we just need to study, is what happens when I try to erase a contour in the presence of a spatially dependent magnetic field. And the first thing that we must notice is that by the GKS inequality, we know that the expectation value of the spin at the site 0 with this field, since it is a positive field, the GKS inequality can be applied. Although it is spatially dependent, the GKS holds in this generality. We know this. So every time, so this is the zero field expectation, and this is with the spatially dependent field, magnetic field. And this means that every time this quantity is positive, this means that this is also positive, and this is no surprise. So since the field is positive, this means that it is trying to magnetize the system to the direction of the field. So in the plus boundary condition, since it agrees with the field, this implies this. So okay, but what happens when we add the field is that there is no spin flip symmetry anymore. So we can't use this chain of inequalities to infer that that this expectation, the sigma 0, now with the spatially dependent field, We can't infer using this what happens to the sign of this. So to have phase transition, one thing that is good to that we want to show is that this quantity is actually less than 0, and this does not imply this over here. So this means that the Pyros argument for spatially dependent field, since the field is always positive, means that we need to make the Pyros argument for the minus boundary condition. So in this case, what happens, since I already did the Pyros argument, I will just show you the competition. Again, the competition between the field and the energy term. This is the energy term, and what happens is the difference of the Hamiltonians with the field when in the minus boundary condition is just the difference without the field. So plus the difference of the spatially dependent field, okay, with respect to these configurations, okay. So here we have something like this. And what is all? This is just, okay, just a reminder of what we did in the last class. So what we did is to calculate this thing over here, and then we got that the difference tau x minus sigma x will be minus the sum of hx 1 plus sigma x inside the support minus 2 times hx sigma x inside the plus interior. Okay? So since we know this quantity already is larger than this, what we get is that this whole thing over here is larger than j gamma minus the sum of the field. Since this can be plus or minus 1, I can bound this. I can give an upper bound by 2, but there is a minus, so this is a lower bound. So there is 2 times x, the support, minus 2, the sum of hx x inside the interior positive. So we need just to analyze the competition. So how we did that? So we started proving the following propositions. So for any finite subset of ZD, we have that the sum, we have that there exists a constant that can depend on delta, h star, and the dimension, okay? It's positive, such that the sum of the field in x inside lambda is less than this constant times the volume with this exponent. So 1 minus delta over d. Okay? And is all good. So okay, how do we prove this? So what we did first was the following. We just started with a ball hx a ball of radius r centered at 0, and then what we had is we divided this into layers. Okay, the ball is divided into layers, and then it appeared some quantity over delta, and x inside, and n starting from 1 to r, where SDN is exactly the points, all the points in ZD, such that its norm is equals to n. So the distance to 0 is exactly n. So the first thing that I want to draw your attention to is what happens to the case where when delta is larger than d. Okay. So if delta is larger than d, what will happen? Okay. We said again. Now I don't quite remember if I gave this as an exercise, but this is in my thesis. I will send it to you. That SDN, there exists constants depending on the dimension, positive, such that this number over here is bounded, is lower bounded by kd times n to the d minus 1, and here it's upper bounded by kd n to the d minus 1. So using this property over here into this sum, what I do get is that this sum is less than the sum n equals to 1 star, that is r, and there will be a k times d, big K times d, 1 over n d minus 1 minus delta. Okay? So what happens in this case when delta is larger than d? It's strictly larger than d. Then if delta is strictly larger than d, this sum over here converges. The sum over here converges. So delta larger than d, then the sum converges. And this means since these terms are positive, okay, if it converges, I can just give the lower bound j times the size of the contour minus 4 times a constant b, where b will be the sum of hx for x in zd. Since this converges for delta larger than d, this is a finite number, okay? And this is just a constant, and for the Pyros argument, it doesn't matter. So last class, I restricted myself to the case where delta was less than d, and this is why. Because if delta is larger than d, it converges, and for the Pyros argument holds without any problem. So consider the case now that delta is less than d. Okay, so what happens in this case is that by using a bound by an integral, I can say that this sum over here will be less than h star kd by, okay, let me do this carefully. So there are two cases that you must consider. The first one is the case that delta is less than d and is larger than d minus 1. Okay, in this range over here, because in this range over here, this means that d minus 1 minus delta will be less than 0, so this sequence is decreasing. Okay, therefore, by using a bound by integral, I have that the sum of n d minus 1 minus delta starting from 1 and going to r is less than the integral starting from 0 and going to r of x, use y d minus 1 minus delta dy, and this is just r d minus delta over d minus delta. And in the case that delta is less than d minus 1, then d minus 1 minus delta is actually positive, so this is increasing with n. And then by using again the bound by integral, this will be less than 1 to r plus 1 of y d minus 1 minus delta dy, and this is just r plus 1 d minus delta minus 1 over d minus delta. Okay, well, there is no need to say that I can assume that r is a positive integer, so larger than 1, okay? So this means that this quantity over here will be actually d minus delta. 1 is larger than r, so this will be less than d, 2 times d minus delta over d minus delta times r times r d minus delta. Okay, so d minus delta is always a positive number, so this 2 to the power of something that is positive will always be larger than 1. So this calculation together with this calculation over here means that this implies that the sum hx sine br 0 xbr 0 less than 2 d minus delta times there is kd times h star r to the power d minus delta. Okay, but I promised something related with the volume. Okay, this is not quite the volume of the ball. Okay, but I know so since I know this inequality over here, so this means that the ball, you can use again another bounded by integral, but there are other methods if you want. This is larger than kd over d times r to the d. Okay, the size of the ball. So this means in particular that I can that r is less than the size of the ball 1 over d times some constants, so the 1 over d kd 1 over d. Okay, and then you plug this over here since this is positive. Okay, so this gives me that this quantity is less than 2 d minus delta big kd 1 over d d 1 over d, so a very ugly constant. Okay, times br 0 1 minus delta over d. This is the thing that we get. So we know the statement for balls, and I stopped last class last week showing how a bound for balls can be translated to a bound for any finite set. Okay, so what will you do is the following. The strategy is to choose your radius r. So a radius r such that hx, when I sum over the ball, is larger than the sum over this finite subset. Okay? So, okay, what I do get is the following. So, first, the sum I can break into two. So everything that I said right before I did last class. So now this is where we stopped. So I can break this sum into two parts. Here, depending on x being inside the ball minus the set lambda, and x being inside the intersection. And I can do the same thing here. X inside the intersection. Okay? And then these two terms are equal, so they cancel out. And then to analyze this difference is the same thing as analyzing this difference over here. So what I can do is the following. So remember that the field is decreasing with the distance, so it is decaying. So this means that if x is inside this ball, since every x has a distance at most r from 0, this means that 1 over x the norm of x, will always be larger than 1 over r. So I can bound this quantity here. I can give a lower bound to this quantity here by the sum, 1 over r to the power delta. But now, since I gave a uniform lower bound, so I have to sum every point inside this set. So this will give me the size of this set. Okay. So now I have to analyze this term. So x is inside lambda minus the ball. So this means that every point here inside this set must have a distance larger than r. So every x here have the distance larger than r. Okay. Why? Because otherwise it would be inside the ball of radius r. So every point here satisfies this. So this means that this sum over here is upper bounded. This sum over here will be upper bounded by, of course there is an h star r to the power delta, okay, times the size of the set. But again, I have a minus sign. So an upper bound to this sum is a lower bound when I multiply by minus. So this means that minus this sum is lower bounded by minus this quantity over here. So summing these two lower bounds, this gives me h star r delta br 0 minus lambda, the size of it, minus lambda minus br 0. Okay. R is positive, h star is positive. So if I want to show that this is positive, I just need to analyze this difference over here. So I will not erase this part. So let's go there. So if I add and subtract the intersection, right, of the two sets, then if I sum both of these quantities, I will just get the size of the ball. And if I sum both of these quantities, I have minus the size of lambda. So in order to that thing to be positive, it is sufficient to have this difference being positive, okay? So if I have this positive, this implies that this difference over here will be positive. So but what happens is that I know that the ball has at least, with respect to the radius, it has this, it's lower bounded by this quantity over here. So in order to this to happen, I just need to choose R. So since the ball has more than kd over the r to the d points, if I choose something, some r that's larger than lambda, so it will be enough. So you just choose r, an integer, right, larger than d over kd times lambda 1 over d. So for instance, you can choose, one can choose the largest, the ceiling is just the largest integer that is, it is the, okay, so where you can choose this, where this is the ceiling function, and this means that it's the number k such that it's the minimum of k, an integer, such that x is smaller than k. So it's the least integer that upper bounds the number x. So this is sufficient to choose to have that thing to be positive. Okay. And what it means for the field is the following. I know that the field over the ball is less than this quantity over here. Okay, less than this quantity over here. So using this upper bound, and this upper bound for lambda, together with this choice of r, okay, then you get, we finally get that the sum of hx, x inside lambda, this will be less than this quantity over here. So d over k over kd size of lambda 1 over d. This is the r. There is all these constants over here. So there is 2 to the power d minus delta kd h star d minus delta. And there is this power over here. So d minus delta. Okay. So one nice property of this ceiling function is that, so check this, is that hx is less than x plus 1, okay? And then by using this x plus 1 over here, we get that the sum is less than and then I have d over kd, 1 over d, 1 over d, the size of lambda, and the size of lambda 1 over d plus 1 d minus delta. Okay, so to finish, to get, you just manipulate this expression. Yeah, so you just manipulate this expression to finish. Just yeah. So what you do, you can do the following. For instance, you know that lambda is a set that has more than one point, and then lambda 1 over d will be larger than 1. Again, since this is a lower bound, so this will give us, by using this will give us 2d minus delta, d minus delta, h star, kd, kd, d 1 over d, kd 1 over d plus 1 times lambda delta minus, 1 minus delta over d. So of course, the constants here are a little bit different, but notice that this constant, there is a d minus delta here. So to have some constant here, this constant here, you just can take the maximum of this and this one. You can see that the constant for the balls are actually better. But okay, so this is proved. So now that you saw what happens in this, I want you to think. So it's not an exercise, just think of, in this case, what happens when delta equals to d. So if you cannot decide what happens, then you can ask me later. Or you can use the Google groups to ask the question. So, okay, so now that proposition is proved, we go back here, and what we do get is the following. Now, in the case that delta is less than d, what we get is that this is larger than j gamma minus 2 times some constant, the support, okay, minus 2 times, here I have 1 minus delta over d minus, here I have minus the interior 1 minus delta over d, okay. And just to finish, we use the isoperimetric inequality, so that we talked about last class. So just remember the isoperimetric says that the isoperimetric inequality says what? Says that for any finite subset of ZD, and D must be larger than 2. This is very important. The dimension is very important here. Then 1 minus 1 over D is less than the interior boundary, the boundary of the interior, or the inner boundary, actually, the inner boundary of lambda. And by using this inequality, this implies that the plus interior will be less than 1 minus delta over d. This inequality here implies that this quantity is actually less than the inner boundary. D minus delta, d minus 1. And since the inner boundary of the interior is less than the support of the contour, d minus delta, d minus 1. And then you just plug this over here. then you get that this is actually larger than j gamma minus 2c gamma 1 minus delta over d plus gamma d minus delta d minus 1. Yeah, so this we did last week exactly. So by analyzing this term and playing with the constants j, for instance, so this you can see that we have different regimes. We have different regimes. If delta is larger than 1, so what happens is that this quantity here, if delta is less than 1, so this quantity here, oh sorry, it's larger than 1. So if delta is larger than 1, then this quantity here is less than 1. So this means that it's actually less than 1. So this quantity can be made positive, for instance, by taking j large. If delta is equal to 1, then this is somewhat a critical case, because we have d minus delta over d minus 1 is exactly 1. So we have a competition between j and the h star. So h star needs to be small, okay? And if delta is less than 1, then if it's less than 1, then this quantity right here will be larger than 1, okay? This coefficient, and this means that the competition will fail, and it's not a coincidence. It fails by a very good reason. It's because there is no phase transition in this case. There is uniqueness. So, Rodrigo. This case, you have uniqueness. So in the case of uniqueness of the Gibbs measure. So this means that there is no phase transition, okay? And of course, the Pyros argument doesn't hold. And if you want to check the proof for this case, there is a proof for beta large phase transition in ferromagnetic models with spatially dependent there is no double T, spatially dependent magnetic field. This is a paper by Rodrigo Pissacco, Márcio Cassandro, Leandro Scioletti e Enrico Pesutti. This is a paper on communications in mathematical physics, 2015. Okay, and what they actually prove in this paper over here, if you want to take a look, is that there is uniqueness, but they need to put a restriction. They need beta to be large, right? Beta large. But we know by let's say by general arguments, for instance, in by a theorem that is known as the Dobrushin uniqueness theorem in Georgi, that not only for Ising systems, but for very general state spaces, there is this theorem called Dobrushin theorems that says that if beta is small, so for beta is small, there will always be uniqueness. So what's happening in this case right now is beta large you have uniqueness, beta small you also have uniqueness by a general argument, by the Dobrushin uniqueness argument, and you can ask what happens in the middle. So since this is a ferromagnetic interaction, okay, it would be very strange if somehow you get phase transition. So what actually happened is that there is no phase transition, and this is shown in just a minute, I'm taking the paper. So last time I didn't talk about this paper, I didn't put the name. It's the paper on JSP with Roberto Villa, right? So the problem of uniqueness in this region was solved. In this region of the field was solved in this paper. So if you want to take a look, graphical representation, presentations for Ising and POTS models and POTS models in general external fields. And this is a paper by Leandro Cioletti and Roberto Villa. It's a paper, the Journal of Statistical Physics, 2016. Okay, so for the nearest neighbor Ising model, the only remaining open problem in this model regarding phase transition is this case. Okay, this is the somewhat critical case. So we don't know what happens when H star is large. So if you that is watching this in the future, maybe you can solve this. Okay, so some comments before we continue. I wanna start. Actually, this result is a result in a paper already. So we are already in research territory right now. So we are going to the heading in the direction of the long-range models, and I want to say a little bit more about this thing. I'll not do any calculations, but what happens now is the following. There is this notion of contours, and you can ask in what kind of generality that I can change my interaction and still get a result of phase transition. Okay, and what happens is that for these contours, if we try to put a long-range interaction, modify the Ising Hamiltonian by a long-range interaction, then the argument will still hold, even finite range. The argument will still hold with some modifications of the contours, of course. But the basic idea of the construction, and what I mean by this is taking connected components of the incorrect points, it will work. It will work also for long-range systems, but with a restriction on the decay of the interaction. So let's say connected contours work also for long range. So let's say work also for finite range, any finite range, okay? And also long range, but with alpha larger than the +1. And this is actually the best you can do with these contours. So since the model, at least since the long range is in model, it makes sense for any alpha, so it's regular, okay? For any alpha larger than d. So you may ask what happens to the regime alpha between d +1 and d. Okay. So for the zero field case, the case with no magnetic field, what happens is that you can use the Griffiths inequality to infer phase transition. So if you have a zero field, so you reestablish the spin flip symmetry that you lost here. You lost with the decaying field. And then you can use the GKS inequality that you can show that every time that the short range model has a phase transition, the nearest neighbor is in a model has a phase transition, then the long range will have phase transition in this region right here. But it is an argument that's kind of indirect because it uses correlation inequalities and does not use a Pardo's argument. And there is another drawback of this kind of argument using correlation inequalities, and is that if I put a decaying field, for instance, if I consider a decaying field in the model with the long range interaction, then there is I cannot use correlation inequalities, okay? So I don't know what happens for the phase transition in this case right here. Okay. And also, not only deterministic fields, if you consider random fields, as we will consider after the conference, you will see at the conference João talking about the random field, and we will see with more details in February. What happens is that you also cannot use correlation inequalities to infer phase transition in this region right here. So we need to modify the construction of contours to access this region here. So this is what I will do now. So okay, so what is the problem with the contours that are connected is that when you break the incorrect points into connected components, then what you are trying to do is to separate the interaction between the parts of the incorrect points. So you need to get a good decomposition of the energy with respect to this breaking of the incorrect points, of this splitting, let's say, of the incorrect points. And the problem is that since the interaction is long range, different from the case of finite range, when you take connected components that are sufficiently far apart, then the interaction, the points will not see each other. But in the case of a long range interaction, it's not important that you are taking something distance. So every time you get something that are not connected, there will still be an interaction. Okay? And if these two quantities here are very large, then there are many interactions. There are many interactions, and so there is a problem, because even if these two quantities are far, if they are very huge, their interaction may be also huge. Okay? So in order to get a sensible definition of contours in this case, we need to get a splitting of the incorrect points we talked last week, in a way that we can control the interaction between the parts of the contours. So of something that we will call a contour. And the following construction that I will show to you, first the definition and then the construction, was this version that I will show to you. It's actually one of the contributions in João thesis. Okay, so João Maia thesis. Okay, there are many Joãos. João Maia. Okay, so the idea is the following. So he defined the concept of a MA delta. So you consider these three real numbers, okay, positive real numbers, and then you define an MA delta partition. Okay, and this is something that that is defined for any finite subset. So given a finite subset of the D, an MA delta partition let's say gamma A is a collection of sets such that they must satisfy two important conditions. The first is condition, let me take color chalk so yellow. A, the first thing is they form a partition, so they form a partition. Okay, they form a partition. So what this means is that for any distinct pairs of elements inside here, they are disjoint. Okay, they are disjoint. They are distinct. and their union is exactly A. And also they need to satisfy a geometric property that is important, is that the following. So for any moreover, for any pair of distinct elements, so gamma is contained in a unique connected component of the complement of the other set. Okay, so what this means is the following. So if, for instance, let's say that your set is something like this. Something like this. And then you have, let's see. Okay, green. And then you have your set A is something like this, and you want to make a partition of it defined by the colors. So in this case, your set A is the whole thing, so it's the mask with the eyes, okay? And you want to make a partition that is the following. You take gamma to be this one, and then you take gamma prime to be these two, the eyes of this drawing right here. So this will not satisfy condition A. Why? Because if you take gamma and you look at the complement is composed by this black area of the blackboard, okay? And what happens that in the complement we have three connected components. We have this unbounded one, we have this component between the yellow and the green part, and we also have this third one between these parts here also. And what is happening here is that gamma prime is living in two different connected components. We don't want this to happen. So this is an example of something that a partition that does not satisfy condition A. So in order to this partition to satisfy condition A, I need to break the green set into two different parts. This is condition A. And condition B is the following. So condition B is the following. So the distance, so just for you to remember, the distance for any, just for you to remember, so remember, the distance between two sets is the minimum of x minus y, okay? I'm assuming A and B, finite, okay? So you take two finite subsets and you take the minimum of this distance when x is in A and y is in B. So this is the distance. And the condition B is a condition on separation. This asks that the distance between the elements of the partition should be larger than m times the minimum of their volume through some power, and the power is A over delta. Okay. So what is happening here, so you can understand, is the following. So if a contour has a very large volume, if it has a very large volume, so it must be sufficiently separated from the rest of the elements of the partition. Okay, and this is the quantity that allows us to control the interaction between these terms right here. But there is a problem, because when you put this condition, you completely loses the geometric interpretation of connected sets of ZD. So the geometry of these things are quite strange, because they are subsets that are not connected. But this condition is strong enough to guarantee some good properties with respect to the entropy. So counting sets that satisfies something like this it's nice. And for these calculations, we will use the multiscale techniques. So okay. And another B implies A when you have B implies A when you have U and João Maia. Okay, when you have the finest, right? Yeah, the finest. You need the finest. Okay. So yeah. So of course there are many. You cannot guarantee that this partition is unique. Okay. The partition just to satisfy something like this to be something that we want to, but we can always construct a finest one. I will prove this, and then what Kelvin is telling us is that when you have the finest one, you just need to ask condition B. This just is sufficient. Yeah, we need to check. Actually, this is something similar as Imri did in his paper. Yeah, actually, because if you look at Froelich and Spencer papers, the unidimensional one, there is that arithmetic condition, and he shows that the arithmetic condition follows if you ask the contours. He calls it irreducible, but irreducible means the finest partition. So if you ask the partition to be the finest one, then that condition also follows. And condition A is kind of something like this. So we need to check, but it's not. Yeah, we definitely can erase it. Yeah, exactly. The final version of this paper, the last one. Yeah. And even for the cluster expansion, you can erase it. Yes. So okay. Another comment about these quantities right here, m, a, and delta. M will be a constant that is large. We will take it to be large, but depending only on the decaying parameter and the dimension. Okay, so we will not worry about this concept right now. Delta is a parameter that is here. It works in this definition. You can define it like this, but in the applications, we take it to be d plus 1. D plus 1, it's sufficient. And when we take it to be d plus 1, delta equals to be d plus 1, then we erase delta from this definition, and we call it just an MA partition. A partition. So, what else? And A is a parameter. A is a parameter that depends only on alpha and D. Okay, and we can take it. It should be, for instance, this condition right here. This condition right here is sufficient. So you take 3 d plus 1 over alpha minus d over the minimum of alpha minus d and 1. This is sufficient, okay? And why? What is happening here, and I want you to understand also, is that the A parameter controls how distant things must be. What is happening is that when alpha is closer to minus d, okay, when alpha is closer to d, this means that the interaction will become stronger, okay. When alpha is going to d, the interaction is becoming stronger. So if the interaction is becoming stronger, this parameter alpha minus d is becoming smaller. So since it is dividing something, this means that all this quantity A is becoming larger when alpha is going to d. Okay, so this is diverging actually. So what happens is that this definition is sensible, is good, exactly on this region right here. Because what it do is that what it does, it says that, okay, when the interaction is stronger, the contours must be much farther apart. They must be much more separated. Okay. This is the interpretation of the A. And okay. So let's see. Okay. I'll do the following. I want to work a little bit on my presentation, so I will stop right now, and then we start tomorrow by proving some properties on that partition. Okay, so